Hello everyone, I'm Norman Walberger and welcome to the Algebraic Calculus. In this video we're going to start moving towards discrete calculus, which is the calculus of sequences. It turns out that defining a general sequence is rather challenging, so we will aim towards introducing specialized kinds of sequences. But today it's just going to be a general introduction, so I don't want to get into that level of detail. But nevertheless, a good place to start is with an informal dictionary type of definition of a sequence. A sequence is a set of related events, movements, or items that follow each other in a particular order. Here is a very famous sequence called the sequence of Catalan numbers. It's a sequence of natural numbers starting 1, 1, 2, 5, 14, 42, 132, and then it carries on in some fashion or another, which is certainly not obvious from the sequence. And it's a great challenge, if you haven't seen the sequence, to try to figure out what the pattern is and how it keeps going. Not easy at all. Okay, so we are interested in this kind of thing, sequences of natural numbers or integers, but we're also thinking about sequences of points, for example, sequences of other things. So for example, this kind of thing where we have a sequence of points in some kind of specified order in the plane representing some kind of discretized motion is also something that we're going to be interested in. So we want to do calculus with these kinds of objects. So this development usually is attributed to early 17th century mathematicians Fermat, Barrow, Leibniz, Newton, and the first book on the subject was by Brooke Taylor around 1715. And this is called the Calculus of Differences, and let me explain why that is. We'll start with this informal approach. We have some sequence S, and that's represented by a list of, in this case, integers. And we list these integers up to a certain point, and then we get tired of listing, and then we just put 3 dots, representing the fact that it goes on to some extent. Okay, so what can we do with such a sequence? Well, in the calculus of differences, there's kind of 2 crucial things that we can do. And they're both denoted by Greek letters. So the delta of S, is a new sequence whose terms are A1 minus A0, the difference here, then A2 minus A1, the difference here, and then A3 minus A2, the difference there, and so on. So this is a sequence of differences, successive differences of the original sequence. And because there's differences involved or changes, the delta symbol is perfectly reasonable. And then the other important operation at this level is the summation operation, denoted by a sigma. So sigma of S, the same S, is the following new sequence. The sequence that starts with 0, and then the next term is A0, and then the next term is A0 plus A1, and then the next term is A0 plus A1 plus A2. So at each stage, we're summing up more and more terms of the initial sequence. So delta and sigma, difference and summation, are operations on sequences. They take a sequence and they give us 2 new sequences. From my understanding of the history of the story, it's actually somebody else, not the people that I've mentioned, that really started the subject, who first understood that there was this difference calculus floating around. And that was the English mathematician Thomas Harriot, who lived from 1560 to 1621. And he's generally given very little credit for things because, for one reason or another, he didn't write down a lot of the mathematics that he discovered. There's a lot of manuscripts floating around, but he didn't publish them. He was a very interesting fellow. He lived a fascinating life. He ended up being a good friend of Sir Walter Raleigh, whose political career went in ups and downs and ended up being executed. And he also sailed to the New World with Sir Francis Drake, I think, and was quite a well-rounded individual in lots of different directions. But in any case, we're interested in the story because he was really the first one to introduce the idea of a difference table, the idea of studying sequences by looking at differences and summations. And the actual sequence that he was actually really interested in was an issue that we've already talked about, which is the issue of sums of powers. In this case, the sum of fourth powers. So the sum of the kth powers, k equals 1, 2, and 3, were known in antiquity, but the fourth power was more challenging. And he worked on it, so he wrote down the fourth powers as a sequence. And over to the right here, we have delta of s. So this is the difference sequence of s. So how do we obtain it? Well, the 0th one is the first one minus the 0th one. That's 1. The 15 is 16 minus 1. The 65 is 81 minus 16, and so on. That's this difference. That's this difference. Notice that's as far as we go because we've only computed this sequence up to 6 to the 4th, so we can only compute the differences up to this term here. And then here is the difference of the difference sequence. So it's the difference of this sequence. And we can write that by using the notation delta squared of s. That means the difference of the difference of s. So the difference here is 14, difference here is 50, difference here is 110, and so on. And then there's nothing to prevent us to keep on going. So here is delta cubed, the difference between these ones, 36, 60, 84, 108, and then delta to the 4th. And now the differences start getting more regular. Here we see 24, and then another 24, and another 24. And at this stage, the pattern is kind of clear. So even if we didn't know what the pattern was that generated this sequence, we could now carry on the sequence just by extending this difference table. So how could we extend this sequence here if we didn't know that it was generated this way? We just had these values. We could do the following. We could say, all right, so the pattern at this level is very obvious. The next one has to be 24. What does that tell us about this sequence? Well, this 24 should be the difference between this and this. So if we just add 24 to 108, we should get the next element in this sequence, which would then be 132. It's the same way that this 108 is 84 plus 24. Same way that the 110 is 50 plus 60, and so on. Okay, once we have this one, that will be the difference between what's next here and 302. So to get this next one, we just add these two, which will be 334. Then to get the next one in this sequence, we add these two, and we get, there's a 5, and then there'll be a 10 carry, and then it'll be 1005, I guess. And so finally, if we want to know what the next one here is, it should be, add these two, we get a 1, and then a 0, carry a 1, gives us a 3, and then 2. So as I mentioned, Harriot was not just interested in differences, he was also interested in summation. And one of his discoveries, really important discovery, is the role of what we've formerly called the Pascal matrix or array. And that this array fits very naturally into this framework of differences and summations. But now we're going to read it from left to right in terms of summation. So previously differences, now summation. And the sequence that we're starting with is the simplest, arguably, of all. It's a sequence of just a constant ones. So that's S. Here's our name for it, but we'll explain that later. And what we're going to do now is successively take summations of sequences. So I remind you that to take the summation of a sequence, this is the 0th one. The first thing that we always do, no matter what this is we write down a 0. That's just what the rule is. And then the next one is the sum of the first one. The next one is the sum of the first 2. The next one is the sum of the first 3, and so on. So it's kind of obvious we're just getting the sequence of natural numbers there. So that's summation of S. And then the summation of the summation, which we'll denote by summation squared, is this one here. So we write down a 0 automatically. And then the sum of the first terms, the sum of the first 2 terms, the sum of the first 3 terms, the sum of the first 4 terms, and so on. We're getting the triangular numbers. So this 15 here represents a sum in this sequence of the numbers from 0 up to 5. And then having that one, we take the summation of this sequence, getting summation cubed of the original, and that's then these numbers 0, 0, 0, 1, 4, 10, 20, 35, 56, and then here are the fourth summations, and then the fifth summations, and we could keep on going here. And the matrix that appears right here, the matrix, is what we formerly called the Pascal matrix, or perhaps we've looked at some finite top corner of it. And we've denoted it by P, but now we're going to attribute it a little bit more fairly to Harriot. So I want to change our point of view towards this array. First of all, Pascal, brilliant mathematician though he was, and very innovative thinker, he doesn't deserve quite as much credit for the Pascal array as he gets. First of all, Chinese mathematicians had this array 300 or 400 years before Pascal, and Al-Khwarizmi, a Persian mathematician 600 years earlier, had an understanding of this array. So it really goes back to other people. But in modern times, this array, in the context of a summation table of successive summations of sequences, which is how we're going to think about it, is definitely due to Harriot, who almost gets no press and no acknowledgement of his contributions. So we are going to change that. We're going to call this array H. And now it's an array that's like a two-dimensional version of a sequence. So whatever a sequence is with its sort of ongoing nature, this is going to be a two-dimensional version of it, because any of one of these columns just keeps on going in some fashion or another, and the rows also keep on going. So this thing extends, has a top and a left-hand side, and otherwise it extends down and to the right as far as you're able to write stuff down. And we'll refer to it as H. So the columns of Harriot's triangular summation table are very, very important. So we're going to give them some names, the columns. H0 will be the column consisting of ones, or it's the sequence consisting of ones. 1, 1, 1, 1. The next column, H1, is just the sequence of natural numbers, 0, 1, 2, so on. The next column, H2, is the sequence of triangular numbers, 0, 0, 1, 3, 6, 10. Notice that when I'm writing a sequence in the usual fashion like this, I'm quite happy to write it horizontally because that accords with the way we like to write things. But when we're making a computation, like a difference or a summation computation for the sequence, we'll tend to write the sequences as down. You can think about that as sort of corresponding to an Excel spreadsheet. Okay, and we will be talking about spreadsheets. So it's kind of convenient to have our data organized flowing down. So, but to write it like this, it's more compact if I write it horizontally. Okay, and this triangular sequence of numbers, of course, has a binomial expansion. You can write it as n choose 2. More specifically, as n times n minus 1 over 2, or 2 factorial. Then the third column, H3, it's n choose 3. The numbers of the form n times n minus 1 times n minus 2 over 3 factorial, 0, 0, 0, 1, 4, 10, and so on. These are the pyramidal numbers. And it goes on, and the kth one, more generally, is the sequence whose nth term is n choose k, where n choose k, I remind you, is n times n minus 1, product all the way down to n minus k plus 1 over k factorial. Now, this particular combination is rather important. This kind of multiplication of a natural number with the one less than it, and then the one less than that, and the one less than that, down to a total of k of them. That's commonly used enough that it's nice to have a separate notation for it. And historically, there are many different kinds of recommendations or suggestions as to what this should be called. But I think the best one is the one suggested by Donald Knuth, which is this notation here, that we'll write n to the power k with a bar underneath it. And we'll say this is n to the k falling. Okay? So there's k products here in this numerator. And those k products are not all equal, as they would be if it was n to the k. They're falling, so it's n times n minus 1 down to n minus k plus 1. So there it is there. N to the k falling is n times n minus 1 down to n minus k plus 1. That's a convenient notation. And then h sub k is the sequence given by n to the k falling over k factorial. So I'm introducing you to a fair amount of new notation. That's going to be important. So let's go slowly here. These sequences, these triangular or binomial sequences that Harriot identifies, these columns of the Pascal matrix H, they themselves form a sequence. Okay, so there's H0, and then there's H1, and then there's H2, and so on. And these are all sequences generated by polynomials in n of degree 0, 1, 2, and so on. And it's useful to give some notation here which brings together the sequence aspect of these sequences with the role they play in this larger matrix that they form. So let's introduce the following notation. So let's introduce h sub nk. So just h with two indices underneath it. This is by definition h sub k of n. Now, both these indices, k and n, are integers which are natural numbers, 0, 1, 2, and so on. So what this is the nth term of the sequence h sub k. And we know what this is because we know what h sub k is. It's just the binomial coefficient n choose k. So we're giving another name to this thing as h sub nk. And the reason why we want to do this is because then we can refer to this element as an entry of this matrix H. Okay, here is our Pascal matrix now called H, and we're thinking of it as some kind of two-dimensional analog of an ongoing sequence. So it's not a finite object anymore. It's something that sort of extends in a way that's maybe a little bit mysterious to us still. But the table itself is just the usual Pascal triangle written in exactly this way. And the columns here are H0, and then H1, and then H2, and so on. And what we're doing here is we're saying, all right, the nth one in this kth column, so if we take the kth column, maybe the second column, then the nth one in this is going to be Hn2 in this case, because k is 2. And that corresponds to the usual notation that we have for indexing matrices, entries. Maybe I will clarify that here. So that over here, the column is indexed by a k, while the row is indexed by an n. So this entry 4, for example here, that would be the case where n is 0, 1, 2, 3, 4, n is 4, and k is 0, 1, 2, 3. So that would be h sub 4, 3, which is the usual way you would read this matrix if you were remembering that the indexing starts with 0. So you denote the row number first, and then you write down the column number, and that's the index. All right, so we have this picture that this matrix H now, this sort of ongoing sequential kind of matrix, is composed of these numbers h and k, in the sense that these numbers here, these binomial coefficients n choose k, are the general entries of this matrix. But we're going to think about it as a matrix of sequences like this, where each one is the summation of the previous one. And so one of the things that Harriot identified about this story is that though you may be generating these columns by summation, if you go the other way, you're getting differences. Or put it another way, that for k equals 1, 2, 3, or something like that, the difference of the sequence hk is exactly the sequence h sub k minus 1. The difference of hk is hk minus 1. Okay, so let's prove this. The definition of the sequence hk, what is it? So the nth term in the sequence is n choose k. N choose k. So the difference of hk of n. How do you take the difference of a sequence? You take the sequence at n plus 1 and you subtract the value at n. So this term here is n plus 1 choose k. This term is n choose k. So n plus 1 choose k minus n choose k. But now it's fundamental property of the binomial coefficients that this thing is equal to n choose k plus n choose k minus 1. So this difference is exactly n choose k minus 1 by the fundamental property of the binomial coefficients. And this is h sub k minus 1 of n. And I remind you that we've already observed that to generate the columns moving from left to right, we're proceeding by summation. So the summation of hk minus 1 is h sub k. So if we think of these columns, h0, h1, h2, h3, in the big matrix H, then we have the situation that going from one column to the one directly to the right of it is applying the summation operation sigma. So sigma gets us from h0 to h1, from h1 to h2, from h2 to h3. And going from one of these to the previous is applying the delta operation. Delta of h3 is h2, delta of h2 is h1, delta of h1 is h0. Now we can put the idea of difference and summation together for any sequence. So if we have any sequence S, then we can generate a table which we might call a difference summation table, which contains both differences and summations. So for example, suppose that we just arbitrarily choose a sequence 1, 1, 3, 13, 37, 81. Well, maybe this is not so arbitrary. So I've chosen some sequence like this, and it goes on. So let's put 3 dots there. Okay, it goes on in some fashion. So we can represent that if we're going to work with this sequence as a column. So there it is as a column. So there's 2 things we can do. We can perform differences on this sequence, or we can perform summations. Now, in the previous, when we talked about difference tables, we went to the right, and when we talked about summations, we also went to the right, because it's easier to write from left to right for most of us. But when we're dealing with differences and summations, we want them to go in different directions. So the convention that we're going to adopt is that when we're talking about differences together with summations, we'll have the differences going off to the left and the summations going off to the right. Typically, the summations make things more complicated. So as we go to the right, things get bigger and more complicated. And typically, the differences somehow make things simpler, especially if the sequence is a polynomial one. So, for example, here is the original sequence, and here are the differences of this sequence. 1 minus 1 is 0, 3 minus 1 is 2, 13 minus 3 is 10, 37 minus 13 is 24, 81 minus 37 is 44. And there's no further difference that we can evaluate. This sequence might go on, but we don't know how it goes on, so we must leave that unevaluated. And then the sequence here take its differences, we get this one here. Take the sequence here and take its differences, we get this one, and then zeros and zeros. And so if we were interested in extending this sequence, we'd have a pretty good idea already at this stage here how to carry it on. Okay, and so we could carry on, just make more 6's here, and then transfer those over until we extended here. Now on the other side of S, we generate the summations, and I remind you, those are obtained by starting always with 0 and then adding up successive initial sequences of the given sequence. So the first one, then the first 2, then the first 3, then the first 4, and so on. We keep on adding. Then once we've got that one, we can take the summation of that. We get a new sequence. You can check that it's that one. We can take the summation of that. We get a new sequence. That's that one there. Actually, we could extend this one further. So these summations actually have more input, because once we're here, we can actually generate one further, because this one here is by definition the sum of all of these ones up to 81. Go diagonally now. So the whole thing has a kind of a slanted aspect. We could just carry on in this direction. Things go in this direction. We could carry on all of these, and we could carry on, well, not these ones. As it is, we couldn't carry these ones out because we don't actually have more information, but we can always go in this direction here, and then these things are going to carry on diagonally down. Okay, so we've got the ingredients in place here, differences, summation, and we've identified these important sequences of Harriot. So now we're in a good position to clarify what's really going on here in terms of the actual definitions of the sequences, and then to go deeper into the discrete calculus. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.